Last time we looked at a priori error estimates. We essentially studied how the error with respect to an exact solution was going to reduce, either with h-FEM or p-FEM. We saw that the a priori error estimate for h-FEM looked like this. So the error is basically bounded by some constant and the mesh size to the power of beta h, and we call that beta h the rate of convergence. In p-FEM, the error is bounded by a constant divided by the polynomial interpolation order to the power of beta p, and beta p is what we call the also the rate of convergence. And then we look at the exponential estimate. Remember that p-FEM delivered algebraic convergence for what types of problems? Do you remember this?
Can you repeat the question?
Yeah, so if you remember, we looked at different types of convergence. You have algebraic convergence and exponential convergence. So if the problems were smooth, p-FEM delivered exponential convergence rate. But if the problems were non-smooth, algebraic. Not linear, it really depends on the approximation of the interpolant, but algebraic. So we did not get an improvement. So the exponential rate for p-FEM is shown here. So it's bounded by another constant divided by e to the power of gamma multiplied by n to the power of theta. And remember, if you remember, this theta coefficient is essentially what how fast, right, the rate is actually changing with the number of degrees of freedom n. And then when we looked at all these a priori error estimates, so if you plot logarithm of the mesh size in abscissas versus the logarithm of the error in ordinates, well, you get essentially for h-FEM a straight line, as you see here, with slope beta h that we define as our convergence rate. And well, you can apply the same idea, but expressing the error as a function of the number of degrees of freedom, the total number of degrees of freedom, and then you get a curve that looks like this, where the rate of convergence is beta h over d. And it's very important to know this because actually in the project, in the second exercise of the project, you have to solve a two-dimensional problem. So you may get confused about the rate of convergence that you get. So you're going to think, well, it's actually almost half of what I should get theoretically. Well, it's not half. It's just that you are dividing by the dimensionality of the problem, which in the project is actually a 2D problem. All right. Then we looked at also the algebraic convergence that P would give you for non-smooth problems, and then well, it's essentially a line as well with slope beta p. And we looked at the exponential. So if we applied twice the log to the error and we plot that as a function of the log of the total number of degrees of freedom, what you get is some sort of straight line. And in the book chapter that you see this, right, and numerically you see that there is a line with slope theta, which is basically that coefficient that we discussed here a second ago. Okay, so we looked into this. We made basically a table where we can see immediately the types of convergence that we can get depending on the category of the problem. Remember, there were three categories: smooth problems, and then those were problems in category A. Category B were smooth problems, except for a region of zero measure where things get a bit complicated, right? You may have a singularity, but as long as that singularity is contained in a set of measure 0, then those are also well-behaved problems, if you will, and those were category B. And then category C is pretty much everything that does not lie in those categories, which you may think as, well, a singularity in a region or an area or a volume of non-zero measure, okay? So we did that. Then we look at the a posteriori error estimate. And if you remember, I told you if there is only one thing to get from this course is this, right? Because this gives you the tool so that when you go to the industry and then you're asked to solve a problem, then you have some sort of idea of how you're doing, how your finite element solution is, because you don't have an exact solution in those cases, right? So the a posteriori error estimate is something that we do when we lack the exact solution, and you're going to do this in the second exercise of the project. So you're going to estimate, there is no exact solution for that problem. And then based on that estimate, you can plot your convergence rates, right? And we talked a lot about this a posteriori error estimate, but in essence, you just need to solve a nonlinear equation that we got here at the end, right? And where the exact solution of our problem can be obtained by just having the approximate strain energy of 3 different problems with different mesh sizes. Yeah, and we also saw that you can also express that coefficient Q not only in terms of the mesh size, as you can see here, but also in terms of the number of degrees of freedom. So there is this relationship. So for uniform meshes, this is more or less true. And so you can obtain that Q exponent in terms of the number of degrees of freedom. And that's it. And then finally, we looked at the high order patch tests. And if you remember, we thought about this idea of creating manufactured solutions. So you think about your implementation of p-FEM, you want to verify it, right? And then, well, how do we verify it? Well, if I have my implementation a cubic polynomial, the first thing I would do is to solve the problem with an exact solution that is a cubic polynomial. And therefore, if I get the exact solution, that means that there is no error, I can say that my approximation is good, right? And you would do this with one element. And then the next step would be, well, I'm going to do it with 2 elements. Because in that case, you're no longer testing only the polynomial approximation. You're also testing the assembly part, right? And your bookkeeping, right, on how you are associating your high-order polynomials to your degrees of freedom, right? And, well, if it works for 2 elements, then you keep testing all the things, like if you change the material properties of the bar, that should also work, and so on. Okay, so we looked at this idea of creating a manufactured solution, and well, once you choose the exact solution of a problem, well, you just need to find what would be the pseudo load. So you plug the solution that you obtain into your differential equation, right? And then by applying the divergence of the stress using that exact solution, then you obtain what would be the pseudo body force that you need to use in your approximation, right? And then, of course, then you solve for that problem, and then you have either well, you can have boundary conditions. You can have a pure Dirichlet problem. You can have a mix between Dirichlet and Newman, or you can have a pure Newman. If you remember, we talked about it. When you have a pure Newman problem, you can get an infinite number of solutions because your system is singular, right? You're not discarding rigid body modes, and so you can get the solution up to a constant, okay? All right, so very quick, right, survey of what we did last time. Perhaps last class was the toughest one, but now we're going to get into the P version of the finite element in 2 dimensions, okay? All right, so let's just make a quick schematic here. So imagine that you have actually yeah. So remember that we work always in some master coordinate space. So 1, 2, 3, 4 are going to be my nodes in master coordinate space. And then, of course, here I have my real coordinate system. So this is xy. Well, and in the real system, this is my element, and the nodes can have any numbering, right? So we can have, for instance, as I put here, 10, 11, 30, 31, as just any example, so we can have any number here. But remember that we always work on a parametric space because integration is much easier. Okay, so now what we want is to build a polynomial approximation in this quadrangular element. And it is essentially the same that we have done in 1D, just extrapolated to 2 dimensions, and you can have an arbitrary polynomial interpolation in this element. Okay, but before we go there, we have to talk about 2 spaces that are used in p-FEM. And those are the trunk space and the tensor product space. So we basically have to see how we're going to build our shake functions to come up with higher order approximations. So okay, so we have to pick enrichment functions, and if you remember, in the case of p-FEM in 1D, did we have an isoparametric formulation? Who remembers this? No, it was not isoparametric. How was it? Subparametric, because our geometry was represented linearly. It didn't make any sense at all to use high order interpolants for the geometry. But what in the 2-dimensional case? Do you see any benefit of using something that is non-linear?
You have like a not straight angle.
Yes, exactly. So let's say one of your edges is curved, where you can improve the geometry approximation, right, of the geometry by using a higher than linear interpolant. Now the question I have for you is that going to be isoparametric?
It depends.
Very good. It always depends. On what? There you go. That is the answer. It depends essentially only in the order of your approximation. If my approximation is quadratic, then I use a quadratic interpolant. For the geometry, then I use it's an isoparametric formulation. Now, if my approximation is kinetic and I want to keep quadratic, the geometry is subparametric. And it's essentially, normally people just go for a quadratic approximation. Yeah, just a quadratic approximation is more than enough. So and because normally the geometry has a lower interpolant, a lower polynomial order, then we are still talking about subparametric formulations. Okay. Now I said that there are 2 spaces that normally are we discuss when we build approximation. One is called a trunk space, right? And we denote it by S trunk space of order P, and of course defined on our master element. And this is basically a functional space that is spanned by some functions that we define. Span so we can build this space by the product of c to the power of I and eta to the power of I. Sorry, that's not I, it's j. And then I, j go from 0, 1, all the way up to p. I plus j is equal to 0, 1, p. Yeah.
What does this look like?
Monomials. Yeah. So also C eta if p is equal 1. And C eta and for now, bear with me that in a minute we're going to see this graphically. So I'm not going to write that now, but we're going to look at it in the Pascal triangle. And then the other space that is normally used is a tensor product space. And we denote that S product space of order P, C, P, eta. And the good thing about this space is that you can actually change the approximation in different directions. So, for instance, you have a higher order interpolant only in the direction of C, but you want to keep it in a smaller polynomial order for eta. You are allowed to do that. You can do this, and it's spanned by, again, monomials eta j, and then I equals 0, 1 pip c, and then j 1 p eta. So essentially what we do is we just decouple the approximation in the two directions, right? And I'm gonna borrow, because it's very annoying to do this actually, but I'm going to borrow this figure here so that we have it in the notes. And now you see how this looks like, right? So here we're plotting the Pascal triangle, right? So you have constant at the top here, and then you have linear, you have quadratic approximation, cubic, quartic, quintic, and so on. And then you see how these different spaces are spanned, right? So you immediately see that if I want to use the tensor product space, then I'm looking basically at these terms here, and then at these terms here, and then at these terms here. But again, the tensor product space allows you to decouple the two, so we may actually go into the direction of having something that looks like this, right? Keep in mind that, remember that tensor product spaces, I define two polynomial interpolation orders for each direction. So here I'm showing the 1, 1, and then this one here, this big one, is basically the 3, 3, but there is nothing that prevents me from having a 1, 3, in which case you can have like asymmetric type of representations in the Pascal triangle. Yeah, and the trunk space looks interesting. It looks like a plane, like one of those stealth planes that you see, right? So that is the way these polynomial space are built. Now I must say that the trunk space is more used than the trunk space, than the tensor product space, well, again, you would use a tensor product space if you really have something where you need to use an interpolant in one direction that is higher than in the other direction, and you could think, for instance, of having some sort of problem with a boundary layer, for instance, in fluids, where you really need to capture the behavior much better in one direction than in the other, for instance, just as an example. So let me finish that. Okay, but this is just about spaces. Now the question is, how do we build our approximation, our polynomial high order approximation, in that quadrangle that we saw? Well, there is one way to do it, is we can build the shake functions using what we already know for the 1D. So we're going to take advantage of the Legendre polynomials that we have used, and we're going to use those to build an approximation for the quadrangle. And therefore, we need basically three types of shake functions. We're going to have the nodal shake functions that are exactly the same as the bilinear shake functions of standard H-FEM. And then we're going to build hierarchically on those. Remember that in order to have a high order approximation in p-FEM, we build the approximation hierarchically. So we keep our linear as is, we don't change it, and then we're going to add a quadratic, and on top of that we're going to add a cubic, and so on. That's what we're going to do. So these are the first ones, and these are the same as in standard FEM. And by standard FEM, everybody knows by now that I mean H-FEM, right? And if you remember, perhaps from some other course, and we actually looked at it last class. After the class, we said, well, how do you build these shape functions? So for the quadrangular element, they have this form. Yeah, where the coordinate, this is essentially the coordinate in master space. So going back to our figure here, right? If you see, this is my master element coordinate, and so if I look at this node here, node 1, right, that's going to be my C1 eta 1, right? And for this particular case, well, this is going to have coordinates what? Minus 1, minus 1, right? So I forgot to say that this, of course, is minus 1, minus 1, and this point here is 1, 1, right? Remember that now our integration rule is still going to span between minus 1 and 1, but now we have two directions, okay? That is the only difference. And so when I plug, for instance, if we take the first phi1 is my first shape function, and then this is going to be minus 1 here, right? And this one here is going to be minus 1. So when psi is equal to minus 1 and eta is going to be equal to minus 1, this whole thing here is going to be equal to 4, right? Because, well, 1 plus 1 is 2, times 2 is 4. The value of 4 is equal to 1, which is what I want. I want the value of the shape function to be equal to 1 at that node and 0 in all other nodes. Okay, so these are my vertex modes, right, or my nodal modes, and these are the same as we have in standard H-FEM for the bilinear element, or the so-called Q4 element. Now we're going to look at edge or side modes. And well, there are, for this particular way of building the shape functions, p minus 1 edge shape functions. Okay, so there are p minus 1 edge shape functions associated with each edge, and they vanish at all but one edge. Okay, so of course the one that we're interested, and you can already imagine that, for instance, a quadratic edge function is going to behave quadratically along that edge, and everywhere else in every other edge that's going to be exactly 0. Okay, and we can already use what we know about the shape functions in 1D, because we know how to represent that quadratic interpolant, right? And then the shape function is essentially going to do what? Who has an idea? How can I build a shape function? So say I have in my first edge, between nodes 1 and 2 in the master element, I want to build a parabola, so it's a quadratic, and I want that to be 0 at every other edge. Who has an idea what we can do? Yeah?
You can create like the formula for the parabola in that edge.
Yeah?
And then somehow assume like a linear
Yeah.
distribution till the other edge.
Perfect. That is exactly what you do. Exactly what you do. So you take the polynomial of quadratic order that we used in p-FEM already for 1D to be a quadratic interpolant along that direction. And in the other direction, you just multiply with a linear variation. So it has a maximum value of 1 at the location of the edge, and then it goes down to 0 at the other end. Okay? And we're going to see in a minute how those look like. So phi corresponding to si, which is the edge, as a function of c, and eta is going to be equal to 1/2 of 1 minus eta, and then phi hat. Remember that those are the ones that the notation that we ended up using as a function of c I equals 2 to the p. Remember that linear doesn't make sense anymore, so now we're talking only about quadratic and so forth. And of course, here I am, well, let me finish this, where phi is exactly the same polynomial that we were using before, 1 divided by square root. And remember that we also said that we were going to use this hierarchically. Oh. So 2i minus 1, and then Legendre polynomial I minus L I minus 2 C. Yeah, and of course, if you look at this shake function, the variation is along the quadratic, cubic, quartic variation is along C, right? So therefore, I am basically looking at the edge shake functions of edges 1, 2, and 3, 4, right? Because those are the ones for which the variation happens along the C coordinate. But of course, if I want to look at the edges for which the variation happens along the eta, then of course I have to change this guy by phi of eta, and then this is going to be now 1/2 of 1 minus C, right? And again, remember that this thing here, it's going to be plus or minus depending on which edge I'm looking at. Okay, and this is very well explained in the book. But the idea is that we build the side shake function by just multiplying one linear function in one direction, the one that we're not interested, with a high order approximation in the other direction. And finally, we have the so-called, and I'm going to move okay here, the internal or bubble. And well, you can imagine already that it's called bubble because what can happen? Why would this called bubble modes?
Because you're going to be 0 on the edges.
Yes, that's why. Very good. So these are functions that are just non-zero internally, right? Everywhere along the boundary, they are 0. And for the trunk space, these appear at quartic polynomial and so forth. And for the tensor product space, they show up at greater than quadratic. So here's p-C, p-eta. Okay, and what I'm going to do, again, I'm gonna borrow another figure from the chapter, and then, well, and you can see how they look like. Oh, this is for the triangular elements. So let me cut this. I would put it afterwards. Or actually, let me keep it. I'm making a mess here. These are the ones that I'm interested right now. And you can already immediately see, right? You have the linear shape functions, the bilinear shape functions of the Q4 element, and then we are adding quadratic interpolants along the 4 edges. So yeah, quadratic. So you see that the function is quadratic along one edge, and everywhere else is 0. And then, well, you have here a cubic, a quartic, and a quintic, right? And then for p equals 4, we start to have the first bubble function here. P equals 5, you have 2 bubble functions. And this is the way you build the polynomials for p-FEM. Now, if you introduce these equations in Mathematica, for instance, you can full simplify the expression and they get very, very simple. And that is, again, what you go and you code in the computer if you ever need to do this for whatever reason, right? That's one way to do it. Okay, but as I said, I am going to just place here. Let me just yeah, and I'm going to, for completion, I'm going to copy this one, because this is the one that we use for the Chebyshev polynomials. This is the one that is explained in the book. So it's just to tell you that a similar procedure can be followed to build the polynomial approximation for triangles. And what you see here on top, this one was built on legendary polynomials, and this at the bottom was built using Chebyshev polynomials. Okay, well, there is an important thing that we need to consider when we look at p-FEM, because if you take a look at this edge, for instance, let's talk about this edge here. Say you have 2 elements, 2 contiguous elements, right? And this is going to be on one side, and if I put here next to it another element, I'm going to have a shape function that looks like this, right? You guys see that? Yeah? Okay. Now, there is absolutely no problem here. There is no problem because the functions are symmetric. So if I put this quadratic edge function here and then this one next to it, the approximation is good, it's conforming, so I don't have any jumping displacement. Now, what happens if I do the same with a cubic interpolant? So say you have this one here, and I'm going to basically put something like this, but depending on the way you put that element and the connectivity, you may have the case where the shape functions are actually flipped from one another. And that is a problem because it's actually creating a discontinuity. So we have what we call non-conforming discretization in the sense of the polynomial approximation, right? So in the case of standard p-FEM, a non-conforming discretization is a discretization where you have hanging nodes. In the case here, this non-conforming because, well, the shape functions along that edge are not matching with one another. So this is an issue, right? And we solve that issue very simply by really looking at how the elements are connected along that edge, right? And I mean, there is only one way to connect those edges, right? One way. Either the functions are matching, in which case you have a conforming discretization, or they are not. If they are not, you just flip. It's like you multiply that shape function by -1. And this is like more like an implementation trick that we do, but we need to discuss it, because if you're ever going to implement something like this, then you need to know about it, okay? So I'm gonna say that very quickly with just a remark, so that you know, you are aware of this issue.
What does he say
in the actual implementation? Be careful of non-conforming caveat.
First word.
Caveat? Caveat?
No.
Like warning, like sorry, my handwriting is not optimal. And again, we look at only the odd shape functions, because for the even shape functions, they are symmetric. They are the same. And then the solution. Well, one solution that works pretty well, we just use the normal to the element, right, to detect what is the direction. And if it just happens that the normal is not in the right direction, we just multiply by -1, and that's it. Okay. Okay. Now, that being said, there is actually a very nice way to handle different types of polynomial interpolation within the element. So you can have, just as an example, well, let's just create something that looks like this. Nope. Yeah. And then let's make, say there is some behavior there, and I want to say, well, this is going to be here p equals 3, and well, in the rest I don't mind. Let's say p equals 2, p equals 2, p equals 1, right? Yeah, so then you can do this or not? Yes, you can. Now, of course, all you need to ensure is that you have, again, a conforming discretization. So then you just need to choose what you are going to enforce along the edges, and that's it. So you can either basically say, well, I'm going to use the minimum rule, and I'm just going to use the minimum of 2 polynomials to enforce along that edge. In this case, would be 2 here, 2 here, 1 here, 1 here. Or I can just pick the maximum, and I'm going to say, well, although this polynomial interpolant here is 2, I'm going to enforce that along the edge. It's going to be a cubic. Yeah?
Do I just basically say that one of the 2 edges that is good, so basically is important, or do I say, for example, for the P3 that on the other 2 edges I have P3 on?
Yeah. So of course you have to look at the edge now. Yes. If you want to have, it's not necessary to have different polynomial interpolants depending on the element, but it can be done, right? So the question is, what do you choose? You just have to be consistent, and you say, well, I'm going to use the minimum of 2 contiguous interpolants. Then you use that rule, or if you want to use the maximum, you can use that too. well, again, okay. And finally, the last ingredient, actually we have two other ingredients to talk about the approximation of p-FEM in 2D. There are two things remaining. We have to talk about the geometry. That's one thing. And then the last thing, which is perhaps the more complicated, is how do we enforce Dirichlet boundary conditions here? And this is an important issue, and who knows why it's an important issue in p-FEM. What have we lost in p-FEM? The partition of unit is lost in p-FEM, and therefore there is another caveat here, because we need to do something to enforce Dirichlet or essential boundary conditions along an edge, right? Remember, all these functions are interacting with one another. Okay, it's not like with Lagrange functions where you can actually pick the function at a node, and then you can enforce that to be the displacement because of the Kronecker delta property. That doesn't hold anymore in p-FEM. So there is something that we need to do there. But let's talk first about the geometry. And then, well, mapping is the last thing we need to do. As we already discussed this, we can have either a linear mapping where x is just xi is the coordinate of node I, and phi is the bilinear shape function. Yeah, and then the other option is to have a quadratic, so you can represent curves. And well, let's say because you have different quadratic representations, but here we're going to use the 8th node, for instance. And notice that I changed the notation of the shape function that we use, because no one prevents us from using different types of functions for the geometry. For instance, I can use for the interpolant for the primal field, I could just nicely use the Legendre-based polynomials. But if I want to use Lagrange type of polynomials for the geometry, I could still do that. And actually many people do that, because then it's nice to place the nodes. So in this case, you're going to have something that looks like this, for instance. Of course, it's going to look curved, but you get the point, right? I'm just doing now so I can draw this, but all these can be curved. Yeah. Well, it turns out that in the book of Szabó and Babuška, they talk yet about a third approach that is called a blending function. So say you have your geometry, you have an exact representation of the geometry, just because you know that the geometry is going to be approximated like a circle or an ellipse or whatever function that you have. It's an exact function. Well, you can also use that blending function, right, to represent the geometry. But this is just to tell you that it can be done, but it is more complicated, of course, to do that type of representation. Now, in that case, when the geometry is represented exactly, then what is the type of approximation that we have? So say I'm using a kinetic polynomial, but my geometry is exact, and it's very complicated geometry. Then, what type of approximation do I have? Super parametric. Okay. And if you are more interested in this, of course, you can check it out in the book of Sabot and Babushka, Circles. Okay, so that is one remaining issue. How do we represent the geometry? And the last issue, and with this we're done with the course. That's as much as we're going to look in this course, is what happened with non-homogeneous Dirichlet boundary conditions. Of course, homogeneous boundary conditions is not an issue, because if we know that along an edge everything's going to be 0, well, that is not a problem, right? Because I know that the linear shape functions are going to be 0, and obviously every other higher order, so the degree of freedom to a higher order coefficient along that edge is also going to be 0. So homogeneous boundary conditions is not a problem. The problem is when you have non-homogeneous boundary conditions. So let's take a look, and I'm going to borrow one more time so that I save some time here. I'm going to borrow that figure. Okay. So say we have that, and you can see here that this is my parent element, and well, for some reason I have a Dirichlet boundary condition that is non-zero along that edge here. So how do we enforce that? This is the main issue. Well, let's see what happens first, so that you know how easy is the use of the Lagrange polynomials. What happens with a Lagrange polynomial, right? Maybe this also contributes to the use of h-FEM more than p-FEM, because for p-FEM, as you will see, we have to solve a local problem to get those coefficients first before we can enforce them. If we're using a Lagrange polynomial, this is automatic, right? You have the Kronecker delta property, and then Dirichlet boundary conditions, regardless of the polynomial interpolation order, are very, very straightforward to prescribe. So if Lagrange well, let's say yeah. Okay. Okay, so now let's say that I have 1, 2, 3, 4, 5. Yeah, so let's just give some numbers so that we can refer that in the text. 2, 6, 10. These are actually the real numbering for the element. Remember that for a Lagrange element, this is not 1, 2, 3, 4, and then you start counting the others. So let me show here. This is going to be eta, and this is psi, and then of course eta 0. So if I start counting eta along this direction, right, I'm going to call this eta at this point eta 0, eta 1, eta 2, eta 3, eta 4. So eta 0 is equal to -1, eta 1 is equal to -0.5, eta 2 is equal to 0, 0.5, eta 4 is equal to 1. And now what I want to do is to enforce let me see. Okay, so I have some function that I need to enforce at those locations. All right, well, so let's write that. How? So that is my function. Let's call it I don't know, let's call it later, I call this gx. We have called also this u bar at some point, but let's call it gx for the time being. Okay, so let's write the equations so that we can enforce these values along this edge that you see here. Well, so what are the shape functions that we have? Well, phi2 of 1 eta, remember that we are at psi equals 1, times u2 plus phi3 of 1 eta multiplied by u3 plus phi6 corresponding to node 6 evaluated along that edge, u6 plus phi10 u10, and then finally phi14 1 eta u14. Okay, well, that is the approximation along the entire edge, but we have a nice property. We have the Kronecker delta property. So if we want to evaluate at the first point, we have u of x 1 eta 0. So what is the only term that contributes to that? Huh? u2. So we have phi2 at 1 eta 0 multiplied by u2, and this of course is going to be equal to u2, because why? Well, because this is equal to, this shape function is equal to 1, so that is equal to u2, and of course that is equal to the value that we're trying to impose, which is g of x evaluated at that location. Right? Well, we can do the same for the other ones. Ux at 1 eta 1. What is the only term that contributes to that? Phi6 1 eta 1 multiplied by u6, which is equal to u6, and then that's a function evaluated at eta 1, and so on. We can keep doing this. So you can see that if you are using Lagrange shape functions, it is as straightforward to implement non-essential Dirichlet boundary conditions as in standard FEM. It's exactly the same thing. Yeah? Okay. So we know those values we prescribe. Now, what if we're using p-hierarchical shape functions? And that is where things get a little bit more complicated. Okay? Okay, let's see what happens. Let's just try to represent that this interpolant, but now we're going to be using the hierarchical shape function. So my u of x 1 eta is going to be equal to phi2 1 comma eta u2 plus phi3. Remember, these are the linear shape functions, right? Plus, let me put them here, plus phi6 u6 plus phi10 u10 plus phi 14 u14. So we said these ones here are my linear vertex modes or functions, and these ones here are what? High order. So these are my edge shape functions, or edge, let's call them again edge modes here. Yeah, well, and if these are my modes, then you can immediately recognize that this term here this is basically my, and I don't want to write here because then later when you print this, then it's going to be a bit messy, so I'm going to move it. Let's continue here. Okay, so this is essentially going to be, remember that now we're building hierarchically, right? So now these are the linear modes, and this is going to be my quadratic shape function, this is my cubic, and this is my quartic shape function. Okay, so this shape function in the context of hierarchical p-FEM, we call it phi hat of second order as a function of eta, right? So this is for p equals 2. And this one here is my phi hat of cubic order. This is p equals 3. I'm not writing this nicely. And finally, this one here is my quartic polynomial for p equals 4. Okay, so now we have, you can see the issue, right? The issue is, well, now we have a quartic polynomial along the edge, and we no longer have the Kronecker delta property. So we're going to have to find a way to determine these coefficients here, right? Because when we determine those coefficients, then we can prescribe the values that we obtain. So essentially what we do is we solve a local problem along that edge so that we know what are those coefficients before solving the full system of equations. Yeah, we need to know, we need to prescribe the non-zero essential boundary conditions. And then the question is, well, how do you obtain those coefficients? Well, you already know that the linear ones are very straightforward, right? Linear modes keep the Kronecker delta property, so these ones are very, very straightforward to obtain, right? Now, what happens with the non-linear ones? Well, there are two criteria that you can use. One is that, well, you can just evaluate this expression at some points, right? And then you build a little system of linear equations, and then you solve for the high order ones. Remember, there is really no need to solve for the linear ones because those are the ones that have this nice Kronecker delta property, yeah? But for the nonlinear ones, you just evaluate at some points, and then you assemble. In this particular case, it's going to be a system of what size for this edge? 3 by 3. It's not a 5 by 5 again because the linear ones are known, right? So we assemble a little system that is 3 by 3, and then we solve for U6, U10, and U14. So that is one approach. The other approach that is a bit more fancy is that, well, I can define an error function along this edge, an error function between my approximation and the function that I want to prescribe. And then I can obtain those coefficients by minimizing this error function, some magnitude of this error function. And what I describe in the book is that you can come up with an L2 norm of that error. So essentially it's the error between the approximation that you have and the function that you want to prescribe. And then you do the same. You obtain a small system of equations, 3 by 3, right? Where the whole system has been obtained by minimizing the error between those two functions. So I'm going to write that very, very quickly. because you can find the details in the book, or you want me to go ahead and write it carefully? The details are in the book. So who's up for detailed description? You don't have to use p-FEM ever again. Not in the project. You don't have 2D p-FEM in the project. So who's up for quick? Who's up for detailed? Okay, clear. Okay, so then let me just very quickly then summarize this. And if you are more interested, then you just go to the book and then you look at the details, because again, all of this is very nicely explained. So again, you have two approaches. Approach number one, you use just interpolation at several points. Well, one choice is to interpolate at Gauss-Lobato points. The Gauss-Lobato integration rule, what we have been using so far in numerical quadrature, does not include the endpoints, right? Well, the Gauss-Lobato does include the endpoints for sampling the polynomial. And we use this here because, well, of course, we have the value at the end nodes as well. So that is one option. So we do essentially ux eta I equals to the value of the function. So we just interpolate. Actually 5, but actually I miss here because we have been using 0, so we have 5 of them. And then this would give you 5 equations. But as we discussed, since we know the linear ones, or the linear degrees of freedom, right? We solve for a 3x3 system only. Yeah. And then once you know those, after you solve this local problem, then you proceed as usual. So you prescribe the value and then you solve the system of linear equations. And then the second option, you do an L2 projection of gx, gy, in the case that you're looking also to an edge in the other direction, on the space of edge functions. And again, all I want to say here is that you can obtain those coefficients by minimizing the L2 error or of some error function between what the approximation can give you along the edge. In this case, it's going to be a quadratic polynomial, and the actual function that you need to prescribe. That's it. So you get the main idea. And that's it. That's for the course. This is the last thing that we're going to see in advanced FEM. Are there any questions related to today's lecture? No questions. Okay, we're going to stop here, and then we're going to use the last 15 minutes to address any other issues related to the project or to the content of the entire course. And then, as I said earlier, we're going to arrange a meeting, not next week because I have to give a conference. I have to travel in the Netherlands for a presentation, but the week after we can spend the whole week, the same time we can meet for addressing any issues implementation wise or anything that you want.
So,
yeah.
So like a walk-in hour where we can also.
Yeah, we can meet here. We're gonna see if this room is available, and then we can discuss. things related to the course. So thank you so much, right, for attending. Yay! I'm gonna record that too, so that it is.